Welcome to 5.1, Natural Log Differentiation. So we're going to look at a quick warm-up here where we want to find the integral from 1 to 5 of x to the negative 1 dx. So if we were to graph that function, x to the negative 1, which is 1 over x, we're looking at this blue guy here. But if we were to try to integrate this, what would we get? Well, we would get, negative 1 x to the 0, right? All over 0, and that doesn't work. So what this leads us to is this natural log. All right, so when we take the derivative, take the integral of x to the negative 1, or 1 over x, we're going to end up with our natural log function. So this turns out to be ln of 5, natural log of 5, if we were to look into this. So one thing we do know how to do is we know how to take the integral of x to the n dx when n doesn't equal negative 1, okay? If it doesn't equal negative 1, then we're in the clear. We can integrate it just as we've always been doing. But when n equals negative 1, that leads us to this natural log function. So what we know is the natural log, or the integral from 1 to x of 1 over t dt, or t to the negative 1, equals the natural log of x, ln of x. So what this implies is that the derivative of the natural log is simply 1 over x. So these are things we just have to know, all right? So kind of memorize those guys, and let's dive into some examples here. Well, before diving into some examples, let's talk about what we know and what we don't know so far. So far, after what we just talked about today, is we know how to integrate 1 over x. It equals ln of x. We also know how to take the derivative of the natural log, okay? We also know how to take the derivative of 1 over x. This has nothing to do with natural log, so kind of keep that in mind. One thing we don't know yet is how to integrate the natural log. So we don't know this yet, okay? That's to come, so hold on to your seats, all right? You can lose sleep over that tonight. Now let's go ahead and jump to this first example here. And we're going to take the derivative of the natural log of this function. But before we do that, since we're going to be dealing a lot with logs, pause the video and make sure you get down these log properties and reacquaint yourself with them. Okay, so now diving into this first example, taking the derivative of f of x. The first thing we want to do is let's rewrite 1 over the square root of 2x plus 3 as 2x plus 3 to the negative 1/2. Using that log property of moving powers to be coefficients, we're just rewriting f of x to be negative 1/2 ln of 2x plus 3. Now we're ready to take the derivative. So as we move forward, we can go ahead and say, okay, well, the derivative is going to be negative 1/2. Remember, taking the derivative of natural log, it's 1 over 2x plus 3. But then we can't forget about the chain rule, taking the derivative of what was inside of that 2x plus 3. So then we have to multiply it by 2, and that takes care of our chain rule aspect there. And now when we clean things up, the 2's will cancel, and we'll be left with f prime is equal to negative 1 over 2x plus 3. Looking at this next example, I see f of x equals the natural log of a lot of things going on in here. So what we want to do is we want to use those log properties. Let's divide and conquer this beast, okay? So we can rewrite it as a bunch of log terms being added and subtracted together. So what we end up getting is f of x is equal to 2 ln of x. That takes care of this x squared portion, moving the coefficient out front, plus the natural log of cosine of 2x. So there's our numerator. Now since we're dividing, this is where we're subtracting, and I just subtracted this entire quantity. So we have ln of cotangent of x plus rewriting 1 minus x cubed to the 1/2 and move that 1/2 out front, plus 1/2 ln of 1 minus x cubed. So make sure you understand how we got this. Now you could have simply subtracted ln of cotangent of x and then minus 1/2 ln of 1 minus x cubed, or you can do it as I did here. So now what I want you to do is give it a try. I want you to take the derivative of each of these pieces. Come back and check. Don't forget that chain rule. Okay, so the derivative of 2 ln x is going to be 2 over x. Okay, so ln of x is 1 over x. The derivative of ln of cosine of 2x is 1 over cosine of 2x, but then we can't forget about the chain rule, so take the derivative of cosine, and that's where we get negative sine of 2x, and then we have to use the chain rule yet again for the inside portion, so times 2. Then we have minus this entire quantity, so the derivative of ln of cotangent of x is 1 over cotangent of x. Chain rule. The derivative of cotangent is negative cosecant squared, so remind yourself about all these trig functions. Then plus 1/2, the derivative of ln of 1 over x cubed is 1 over 1 minus x cubed, and then the chain rule of 1 minus x cubed is negative 3x squared. So after that, now it's just a matter of cleaning everything up. And here's what we get as our final answer. Now notice in this second term here, I have the tangent of 2x. Well, we have sine over cosine. So remember, sine over cosine is tangent. And then we can break up 1 over cotangent and cosecant squared. When all is simplified, we really have secant times cosecant, all right? And then cleaning up our last portion there, our last term, we get 3x squared over 1 minus x cubed. This next example, I don't see any natural logs in there, but what we should notice is this is crazy nasty, right? This function here. So to make our lives easier, we actually are going to take the natural log ln of both sides, okay? So it's going to look something like this. Ln of y equals ln of this entire function here. And by doing that, it allows us to break up this right side into many natural log functions or many log terms. Okay, so what is that going to look like? Well, I still have the ln of y on the left, and now we can rewrite the right side. So moving this 3/2 as a coefficient, we have 3/2 natural log of x minus 1. Since we're dividing those those arguments, we're going to subtract the log terms, and instead of x squared plus 1, or the square root of that, it's x squared plus 1 to the 1/2, so we can move that coefficient out front, and then we have ln of x squared plus 1. Now we have to use implicit differentiation to differentiate both sides. So when we take the derivative of that left side, we get 1 over y times y prime. That's that implicit differentiation portion. Taking the derivative of this term here, we get 3/2 times 1 over x minus 1. Thinking about the chain rule, yes, but the derivative of x minus 1 is simply times 1, so we don't need to worry necessarily about writing that aspect. Then minus 1/2 of 1 over x squared plus 1, and then we have to take the derivative of x squared plus 1, and we get 2x. So cleaning up, but at the same time, we need y prime by itself. So what we're going to do is we're going to multiply both sides by y, okay, and cleaning things up. So when we multiply both sides by y, we are left with y prime on the left. Cleaning up the inside of these brackets, we get 3 over 2 times the quantity x minus 1 minus x over x squared plus y, and then we're going to multiply by y. Well, we know what y is because it was given to us at the very beginning, so now we're just going to substitute in for this y here. And when we make that substitution, we get our final answer with that substitution thrown in. So y prime is really equal to this quantity of 3 over 2 times x minus 1 minus x over x squared plus 1 times that original function, x minus 1 to the 3/2 over the square root of x squared plus 1. Lastly, we're going to look at a couple other definitions with e and then absolute value. How do we find the derivative of absolute values? So here, the natural log of e, we can think about it as an integral, all right? If our integral is going from 1 to e of that 1 over t, it's simply the natural log of e. And then we also have the natural log of x equals n. If we were to convert this to exponential, we get e to the n equals x, so then it makes sense that the natural log of x is equal to this n value. All right, absolute value, we can say the derivative of ln of the absolute value of u is 1 over u, and that's if u is greater than 0, then we know the absolute value of u equals u, right? If u is negative, then u prime over u is going to be a negative number over a negative number, which is a positive. So, which means differentiating the natural log of the absolute value of x as if the absolute value bars were not present. So we really don't need to worry about those, is what it is saying, okay? However, let's go ahead and just practice this last example where we are finding the absolute value, we're finding the derivative of y, where y is equal to the natural log of the absolute value of cosecant of x plus cotangent of x. I want you to remember, we don't have to worry about those absolute value bars. Just go ahead and take the derivative. Go ahead and try it on your own and come back and check. Okay, so what we should initially get is, taking the derivative, we get 1 over the cosecant of x plus cotangent of x, and then we have to remember the chain rule. So this is a good reminder of your trig functions. Derivative of cosecant is negative cosecant cotangent. Derivative of cotangent is negative cosecant squared. So now we're going to clean it up, and the way I go through and clean this up is I'm going to rewrite some things. So instead of negative cosecant, I rewrote it as negative 1 over sine of x. Cotangent, remember, is just cosine over sine. And then minus cosecant squared is really like saying 1 over sine squared. And we can do the same thing for the denominator. Cosecant of x is really 1 over sine of x. And cotangent of x is, again, cosine over sine. So what we can do is, if we multiply both the numerator and the denominator by sine squared of x, what we should notice is we will be left with negative 1. I pulled a negative 1 out, okay? But we'll be left with just cosine of x minus, or it's going to turn into a plus 1 because I take out the negative, all right? And then our denominator is going to be, we're going to be left with sine plus sine times cosine. Well, if we factor out a sine, we're just left with 1 plus cosine of x. So these pieces will cancel, and we'll ultimately get our final answer for what y prime is, and that's negative 1 over sine x. So it does simplify nicely. If you do have questions on any of it, let me know.